Hi everyone, my name is Manuel Brenner, and today I want to give you a short rundown over our TMLR paper on uncovering the computational roles of nonlinearity in sequence modeling. Generally speaking, sequence modeling can be decomposed into two classes of models, and also probably in machine learning more generally. On the one hand, you have linear models, which are easy to optimize, easy to analyze, but are somewhat limited in their expressivity, specifically in a sequence modeling context. Easy to optimize means you can parallelize them, you can analytically access their properties like long-term behavior via the stability or their fixed points. And expressivity means they only have three different dynamics you can represent: convergence, cycles, and divergence. On the other hand, nonlinear models are hard to optimize, also closely linked to the exploding and vanishing gradient problem, and hard to analyze because there's no universal analytical expression for them. But on the other hand, they are highly expressive, able to approximate any kind of dynamic and complex operations like contextual processing, multistability, chaos, for instance. So one of the guiding questions in sequence modeling research and machine learning recently has been how much nonlinearity is actually necessary, with Oviedo, for instance, finding that linear recurrence often outperforming nonlinear recurrence on a bunch of sequence modeling tasks. And in general, the success of structured SSMs relying on linear recurrence achieves very strong sequence modeling performance, where you basically discretize the continuous state space and implement long-range dependencies via specific initializations and optimize via these fast discrete convolutional representations, which enable you to optimize in parallel along the whole sequence. But in these architectures, linear recurrence is usually embedded in stacks combined with nonlinear transformations, and there's no clear interpretation of what role these nonlinear transformations play or of an involving state, because you stack multiple layers of these recurrent units. That makes it very hard to understand what kind of, basically from a evolving state kind of perspective, what is happening in the sequence modeling. So taking a step back, we can describe sequence modeling in general as a combination of an input, a recurrence, and an output. And this leads to different task formulations like many-to-one tasks, for instance, classification, one-to-many tasks like captioning an image, for instance, or many-to-many tasks, which is the classic chatbot paradigm that is used in ChatGPT, for instance. In this work, we want to focus on the recurrence specifically, which we conceive of as an evolving dynamical system. So this dynamical systems perspective, it combines a state space in which an evolution takes place, a time evolution given by a function parameterized by an ODE or discrete map. And these discrete maps can, for instance, be represented by a recurrent neural network or a linear dynamical system, as in structured SSMs. And what we achieve through this dynamical systems perspective is a certain interpretability via dynamical objects like the stability. We have an evolving state that basically captures the computation inherent in the recurrence. And this gives us a lot of interpretability and tractability in terms of what is actually happening here. I already mentioned the advantages and disadvantages of linear and nonlinear models. In general, nonlinear sequence models are difficult to analyze. So one idea in the field has been to decompose activity into subregions with linear activity. So you combine the advantages of linear models with the expressivity of nonlinear models. And recently, within this vein, we suggested to restrict nonlinearity of so-called AL-RNNs to a small subset of units, coming up with the almost linear RNN, which is a very simple model in itself. It is basically a linear dynamical system with a ReLU nonlinearity, but this ReLU nonlinearity is only restricted to a subset of states. So you can think of it as very intuitively as a combination of L linear neurons and P piecewise linear neurons. And since these piecewise linear neurons have the ReLU activation function, the activity of the AL-RNN in state space naturally decomposes into the set of 2 to the power of P linear subregions, which can here be assigned a specific code. And as I mentioned, this leads to this nice bitcode representation where we can decompose the state space again into regions of linear activity, and the time evolution of the system itself can be associated with these bitcodes, and then the long-term behavior or the network while it solves tasks can be decomposed in this bitcode representation, where each of the subregions gets assigned a count or a frequency, and this allows us to basically understand in which part of the task solution the network spends in which linear subregions. So this work, we originally, in our NeurIPS paper that suggested this architecture, we looked at dynamical systems more specifically, for instance, finding that we can reconstruct chaotic dynamical systems with only 2 to 3 linear subregions, and where the linear subregions have very clear semantic representations aligning with these so-called topologically minimal representations in the literature, where each linear subregion reconstructs one of the true fixed points or unstable fixed points of the underlying system and creates this chaotic activity via composites of these unstable spirals around these fixed points. So inspired by this, we wanted to ask the question what we can learn about the role of nonlinearity in sequence modeling much more generally. So again, going back to this like taxonomy of different sequence modeling tasks, we looked at a class of different tasks, for instance, classification, the addition task, contextual integration, multitask suite, and so on. And we wanted to really look at, across these different classes of models, for instance, what and how much nonlinearity is acquired across tasks, and can we actually interpret dynamics of the task solutions, but also more specifically, can we understand the computational role nonlinearity plays in solving these tasks. For this, again, the AL-RNN allows us to view nonlinearity as a tunable model component, where we can tune models from fully nonlinear to fully nonlinear and basically explore what happens along the way of increasing nonlinearity in the network. First, we looked at a suite of so-called evidence accumulation or classification tasks where we have either text, images, like in sequential MNIST, or audio, as in speech commands, and we each process these via modality-specific processing and put the inputs into the AL-RNN and then allow it to accumulate evidence over the sequences, and then from its final state come up with a classification of either the sentiment of the IMDb movie review or the final number or the final speech command. And what we find here is that we actually have quite similar structure across all modalities. Where in IMDb, crucially, we find that actually nonlinearity in the network does not improve performance in a statistically significant way. And part of this is that the mechanism underlying this is very simple, where we come up with this nice one-dimensional line attractor that has already been observed in the literature, which only integrates specific keywords like worst or terrible that imply that their review is negative. And this gets basically stored, this information, along this sentiment attractor. And other than that, the activity of the network is not very interesting, and hence we have very simple linear activity that suffices. For sequential MNIST, the trend is somewhat similar, with linear models already achieving very good performance, but nonlinearity achieves a significant improvement by 1.2% roughly accuracy. And we can look at this in the state space of the reconstructed, of the digital classification, and we find that adding nonlinearity to the network separates classes better, but in the fully nonlinear case, we find some of the classes to be quite over-dispersed, and in general, we can link this to the increase of nonlinearity enables the model to implement slightly different integration dynamics for each of the classes. Next, we looked at the addition problem, where the AL-RNN has to add up 2 marked inputs and output their sum at the end. And what we find here is that actually sparse nonlinearity already achieves quite good performance and plateaus, and then for fully nonlinear model, performance actually gets a bit worse again. And part of the explanation for this is that the mechanism solving the addition task is actually super simple. We have linear integration, but when marked inputs occur, they get projected into a different linear subregion where they are summed up, and then the linear integration again occurs. Crucially, this is necessary because the network receives a steady stream of inputs, but only the marked inputs are important. So this is a form of contextual processing. This is only possible with nonlinearity, but the shape of the nonlinearity itself is quite simple. We find this to be true when we look at what actually happens with a bit code distribution for this task for different levels of nonlinearity. So starting with only one nonlinear unit, we find that integration and the basically masked inputs are cleanly separated. So the masked inputs project to a different linear subregion, and while the activity otherwise stays in another subregion. And if we increase the level of nonlinearity, we find that we have this very pronounced distribution that focuses integration on a small subset of units, and the masked inputs are also projected towards another small subset of units. And this even holds for very large latent spaces or levels of nonlinearity, where in principle we would have 2 to the power of p possible subregions. And part of this, again, is that the mechanism underlying this task is quite simple, while the model, basically, if it's fully nonlinear, has too much expressivity and basically spreads out this simple mechanism over many subregions, and which risks overfitting and which risks like not finding the simple task solution. And part of what we find is that the network actually linearizes subunits by pushing the activity either below or always above 0. So the model actively pretty much serves as a linear unit and has to learn to avoid basically the linear, like the nonlinear boundary. Next, we looked at a set of multitask suit where we had different classic tasks from computational neuroscience that the RNN then was jointly trained on. And then we could look at, again, for each specific task, what are the bitcode distributions that we get out? How does the network leverage nonlinearity, and how does it distribute it across different tasks? What we found very interesting here is that sparse nonlinearity provides sample efficiency. So if we only have 20 samples for each task, the sparse nonlinear models actually perform by far the best, while the fully nonlinear models do not train successfully. While if we increase the sample size, the models get better and better. While for the full, if we have 500 samples per task, the fully nonlinear models actually perform best. And one way to understand this is to look at how do models reuse different nonlinear regions. So here we looked at bitcode similarities. So again, we looked at for each task what is the bitcode distribution, and then we looked at a similarity measure of these distributions, and saw that for specific tasks, for instance, in this case, the delay pro and the react pro task, which had quite similar structure, that the model actually uses nonlinearity in a very similar way and can basically cross-learn across these two different tasks. While for the fully nonlinear case, the model basically affords specific nonlinear solutions for each task independently. So in the case of p equals 32 or 64, so most of the units or all of the units being nonlinear, the model actually just implements one independent solution for each task and does not basically crosstalk with other tasks to achieve this transfer learning effect. And this in turn leads to worse performance if you do not have a large sample size. As an outlook, we also looked at several other tasks like the copy task, the scan task of syntactical reasoning, but also cortical spike recordings from a stimulus selection task where a rodent has to basically select stimuli based on active rules and also decide ambiguous cues based on context. And we found recurring structure across all tasks that, for instance, we often have this linear backbone that integrates information or memory and does not actually require nonlinearity. We have then this combined with this sparse nonlinear switching or gating for different tasks. And in general, we find that this combination leads to a useful inductive bias of sparse nonlinearity, because we often need a linear backbone to serve as like a simple function for integration, but we also often need nonlinearity to achieve certain tasks, like in the addition task where this context-dependent addition is not possible if we do not have this nonlinearity in the model. So as a conclusion, the AL-RNN learns these highly interpretable piecewise linear models of sequence tasks, and it actually uncovers computational mechanisms of nonlinearity across a wide range of tasks. And we often find that sparse nonlinearity actually is on par or outperforms full nonlinearity. With that, thank you for your attention, and thanks to our funders.